Okay, welcome to the first video on this channel. This is Introduction to Chemistry at the sophomore level in high school. First thing we have here is chemistry and matter. So let's get right into this. Chemistry came about from philosophers, right? Obviously, it didn't just appear out of nowhere. We have to kind of figure out what is around us, what's going on. So it kind of talks about how small can an object get before it stops being that object. We have questions like, what are the unique traits of different substances? What causes those unique traits, right? So one thing to note is that the study of chemistry is absolutely linked to matter. What's matter? So when we talk about matter, we have essentially two different things here. We've got mixtures versus pure substances. Okay, so the main idea is that matter is defined as any object that has mass and takes up a volume of space. I am matter. You are matter, right? We matter. So matter typically has a particular state it is in. We obviously know what these are: solid, liquid, gas, and those depend on the temperature, which is also called the average kinetic energy, which we will get into later on. So the state of matter affects how the particles of that matter are arranged. So particles will move differently in each state. They'll be closer together, they'll be farther apart, they'll move fast, they'll move slow. It depends on the state, which we'll get into. Shape and volume are different for each state. And so let's get right into it. So solids. Solid is rigid with a definite shape and volume. So strong attractive force between the particles. So when we think about a solid, those particles are kind of moving like this, right? They're not like this, like a gas. They're not going like this. They're really just in place because there's a strong attractive force between those particles. So particles vibrate in fixed positions, as I just demonstrated with my hands, and this picture kind of shows that too. So particles vibrate faster at higher temperatures. Again, the temperature does matter. Liquids. Liquid is a flowing matter with a definite volume that we know takes the shape of its container, not like a solid. So that gives it an indefinite shape because it's just going to fit to whatever container the liquid is placed in. So the forces of attraction keep the particles close together. So unlike a solid, it's not going like this, but it's going like this. They're still close together, but not as close as a solid, right? So as you can see here, it just kind of does whatever the container wants it to do. You spin the container around, it's going to spin. You dump the container, liquid's going to fall out. So volume is constant, of course, and then particles slide past each other, as I just demonstrated. Moving on to gases. So a gas is flowing matter. It has no definite shape. Particles bounce off container walls and each other. They're kind of just going crazy. So with your hands, if you wanted to do that, it would really just be like this. They'd be going everywhere. That's what my chemistry teacher explained it to me. Models of particles in each state. Again, recap. So gas, you have them bouncing everywhere. Liquid, you got them close together, but not as close as a solid, where they're literally just vibrating in those fixed positions. Next up, we have classifying matter by its composition. So, pure substances. Pure substances are matter, or is matter, with the same fixed composition and properties. So, let's say, for example, we have water, H2O, 2 hydrogen and 1 oxygen atom, okay? A mixture. A mixture is a combination of two or more substances in which the basic identity of each substance is not changed. So, for example, pepperoni pizza. A pepperoni pizza is not just one thing. You need a bunch of things to come together to actually make that pizza, right? And there's going to be different amounts of each thing too. So the amount of cheese, the sauce, the pieces of pepperoni, that depends on who's making the pizza. That's not a pure substance. Okay, so that's what's going on between a mixture and a pure substance. And next up, if we compare elements versus compounds, there's initially, before people start chemistry, they have some confusion. So people think, oh, well, water's an element. Well, water's not an element, it's a compound, and we'll get into that right now. So both are pure substances, and so elements, they are one type of atom. Okay, it's not a compound where you have multiple things together. It is one pure substance. It's just one. Like, for example, oxygen, that is an element. And they can only be separated by a nuclear reaction, unlike compounds, which we will see. So these are obviously found in the periodic table, which I will be giving, of course. Compounds are two or more different atoms bonded together, so there are multiple elements, okay? It's not just that one pure thing. It is, of course, a pure substance, but it's multiple together. And these properties are different than its elements. Why are they different? Well, the reason is because an element has individual properties, of course. When you put them together in a compound, those elements are going to kind of vary because you're putting two elements or more together. So the properties are going to be different than their parent elements. And unlike the elements, these can be separated by a normal chemical change, chemical reactions. So copper is an example of an element, and sugar would be an example of a compound because you need different elements to make the sugar, whereas copper is just one element, a pure thing in itself. Both are pure, though, of course. Next up, we have compounds versus mixtures. So compounds are pure substances, mixtures are not. So it's important to differentiate between compounds and mixtures. They sound like they would be similar, but they're really not. Compounds, again, are elements bonded together. Mixtures, you will see here. So most everyday matter occurs as mixtures. It's not like you kind of just have compounds everywhere. Of course, water would be one, but still, even in water, oftentimes you have different chemicals in that water. So combinations of two or more pure substances, that would be a mixture. Individual substances within a mixture keep their properties. So that's important to note, that they keep their properties although they are in the mixture. So mixtures, now honing in on mixtures, they have two subcategories, which you've probably heard of. The pronunciation varies, but I say it as heterogeneous and homogenous mixtures. So, heterogeneous mixture. Obviously, there's kind of like one main way to differentiate these things that pops into our head. You've got a male and female in a relationship, heterogeneous, right? Those are two different ones. So therefore, a heterogeneous mixture does not have a uniform composition, and its individual substances remain distinct throughout the whole mixture, okay? So it's like, we'll have examples here, but you can see the parts. So these parts, the different parts in the mixture are called phases, different phases of a mixture. In lemonade, a lemonade, most of the time, is a heterogeneous mixture because you have two different phases. You have the liquid, but you could have the pulp too. Pulp is one phase, and the liquid itself is another phase. So these are caused by differences in the properties themselves, that they can't mix together fully. So olive oil, vinegar, and then oil and vinegar, that's a heterogeneous mixture, right? In the two different phases, you can see them here, this top phase versus this bottom phase, the oil and the vinegar. Oil and the vinegar. M&M's, heterogeneous mixture, right? First of all, you have different colors, of course, but that's not all one thing. Classifying mixtures. Now we have a homogeneous mixture, okay? So this always has a uniform composition, and it is the same throughout no matter what you do. You take a cup of this mixture, it's going to be the same as if you took another cup. It's homogeneous. Individual parts still keep their properties, of course. Examples, so salt water, Kool-Aid, air. Why? Because first of all, salt water, the salt dissolves. It's going to be the same no matter how much of that water you take, you're going to have the same. Kool-Aid, you mix in that Kool-Aid packet, it's going to be the same. Air, you're going to have the same amount or percentages of each of that stuff, nitrogen, whatever's in the air, nitrogen, oxygen, even carbon dioxide. It's going to be the same. It's homogeneous. Right, so we've got Kool-Aid. Next, we have atomic scale in pictoscopic models, okay? So, elements, compounds, and mixtures. That's just kind of what we went over, if you were to give it that scientific name. So, again, elements and compounds, pure substances. Mixtures are not pure substances. And when you go down from mixtures, you got homogeneous and heterogeneous. And this is a good picture to kind of explain that difference here. Next up, we got extensive versus intensive properties. So, going over this, an extensive property, that is a quality of the substance that changes if you have more or less of it. Okay, so for example, mass and volume. Let's say I have water. The extensive property would be mass because that mass changes depending on how much water I have, right? Same thing with volume, same thing with surface area of something. So an intensive property is exactly the opposite. It doesn't change if you have more or less in substance, right? The color of something, if I have an apple and I cut it in half, well, the color's not going to change, right? So pretty simple. Temperature, same thing, density. Density is maybe one that can be confusing sometimes, but let's just say I have this thing here, whatever this is, the particles, cut it in half, and that density doesn't change, right? So that's that. Now we have physical properties. and chemical properties, which will be after. So physical properties. So these are pretty obvious, of course, because they can be observed without changing the substance into a different chemical substance. So physical change then would be when the form or appearance of matter changes, but the chemical substance remains the same. Okay, so you can change something about that substance, but essentially, like chemically, the makeup is the same. Nothing really chemically changed. It just physically changed to our eyes. Now, physical attributes or physical traits would be appearance, right? Color, texture, state of matter, solid, liquid, gas, size, and then behavior, the viscosity, melting point, boiling point, solubility. Solubility we know is how much will dissolve in water. Density, magnetism, those are physical traits because that is just like a trait of me and you. How nice am I? How mean am I? Right? Physical change examples. So this one can be confusing at times for certain reactions. So making ice, liquid to solid water. Did a chemical change occur when you made ice? No. You just changed the state of matter. And if we go back here, you see solid, liquid, or gas. That is a physical attribute. Crushing an aluminum can. You didn't change any chemical makeup, you just changed the appearance. Again, it goes into appearance. Mixing oil and water. This one, when you start to get into mixing, students can sometimes be like, well, okay, but you're mixing. But you did mix, but nothing changed, right? You didn't have a new product. And that's one of the key signs of a chemical change or chemical reaction, is when a new substance is created. In this, no new substance was created. Even if you're mixing, you're not making anything new. Filtering pasta from cooking water, okay, you're just separating some stuff, not making anything new. Physical properties can be used to separate mixtures, okay? That's an important thing to know. Don't get confused by that. Chemical, so chemical property, only observed by changing the chemical composition of the substance, as I just went over. So chemical change. When the chemical composition of a substance changes, this, as I said, can also be called a chemical reaction. Chemical change, chemical reaction. Pretty much all the time, you're only going to hear chemical reaction. You're not going to hear anyone say chemical change. Now, going into chemical properties, the chemical properties, I'd say, obviously the whole chemical aspect of these properties and changes is more important than the physical because they can be harder to identify. So, ability of a substance to change into another substance, or create another substance. To observe/measure, substance will change into something else. That's the only way you're going to be able to measure that, right? So chemical properties, examples. Flammability. How capable is something to catch on fire? Tendency of material to burn, of course. Reactivity. How does it even react with other stuff? With oxygen and air. For example, rusting, a car rusting with the oxygen. With light, right? Milk breaking down from the light, or, rotting, as we would say. With acid, how does it react with acid? With water, with all of these different things. But oftentimes, just because something doesn't have any reactivity or any of these traits, these are just specific traits, doesn't mean it's not going to be a chemical property, right? So, by the way, if it doesn't react with anything, it's called inert. That is the name for non-reactive. Elements in the same column of the periodic table have similar reactivity. So periodicity is going to be a whole unit in this course in chemistry. But just as a kind of basic reminder, elements in the same column of the periodic table have similar reactivity to each other. And there's obviously many, many patterns we will get into with the periodic table. So here's that. Chemical changes. So there's going to be different signs when a chemical or substance undergoes a change, right? When it changes into a new substance with different properties than the original. That's what makes it a chemical change. A new substance that has different properties. Again, also called a chemical reaction, and it must form a new substance. If a new substance was not formed, as I mentioned, this was not a chemical change or reaction. Example. So, paper burns producing ash and gases. That would be a chemical change or reaction. Why? Because you produced ash and you produced more gas. Rusting of a steel bicycle or car. The act of rusting, I'm sure we would all just could guess that. Rusting doesn't just come out of nowhere. You had to have a chemical reaction between oxygen and the metal for something to rust. Iron, right? Forming carbon dioxide from baking soda as a cake cooks in the oven, or even just baking soda and vinegar. When it fizzes up, fizzing is a sign of gas being released. Even if you can't see the gas, there is a gas being released when something is fizzing. That would be a chemical change. And a gas is not just gas, it has its own chemical makeup, so that is a new substance in itself. Chemical change indicators, or signs, right? Clues that a chemical change might be happening. So, as I said, a solid forming, of course, or a gas forming. Don't just neglect a gas. A gas is a key sign, and that's most of the time when you react to stuff, you're more likely to get a gas. Not boiling or freezing, okay? Because as we discussed before, boiling in itself, or boiling point, that's a physical attribute, right? The boiling point or melting point of something, that's physical. So boiling or freezing has nothing to do with chemical change. You're not making anything new. You're just kind of changing something. If I had water and I froze it, I'm not changing the water again, right? So major change in color or odor. So once the appearance changes, that's different in terms of color or smell, because that's an indicator that something had to have reacted with it and created something else, such as the new odor. Bleaching or fermenting. Rapid release of energy. So energy, we know, comes in different forms. It can come in sound, it can come in heat, it can come in light. Gas releasing, that's obviously a form of energy. And again, we're really stressing that the fact a different substance must form for the chemical change or reaction to actually have happened. Next up, we got separating mixtures. This is the last part of this video. The most common ways in chemistry in which we separate mixtures would be filtering things, a method called chromatography, and evaporation. Okay, and these are kind of different ways in which those are done. So filtering is used when, and again, separating mixtures would be not a chemical change, but a physical change, right? So filtering is used when a heterogeneous mixture, for a heterogeneous mixture of a solid and a liquid. That's when filtering would be most appropriate. Chromatography is almost always used on homogeneous mixtures. So as you can see here through this, it's basically separating these, most of the time, homogeneous mixtures through a different material, a third party, if you will. So that's how you can do that, putting a paper, right? So this causes different components to flow through the material at different speeds so that they actually end up separating. So again, evaporation, most of the time homogeneous mixture of a solid and liquid, like a mixed drink. We know what evaporation is. Decanting, of course, is one of these methods. Centrifuging and distilling. So decanting is when most of the time used when there's two heterogeneous liquids. Centrifuging to separate suspensions. Suspensions you can kind of think of as phases. That's a different way to do that. And distilling, most of the time two homogeneous mixed liquids. And so, of course, another way to do it is sorting by unique property. That's a different way you can separate mixtures. Color, shape, size, magnetism. That's obviously a way to separate mixtures. But we have different photos here to kind of explaining each of those. This would be centrifuging. Distilling is right here, and this is decanting. Decanting is kind of when you're swishing something around so fast that it separates, like with plasma in the hospitals with the blood. That's how they do it. They have those big machines that spin around the blood so fast that it separates the cells, if you will. So that is separating mixtures. I think the hardest part of this unit would probably be just kind of understanding these separating mixture techniques, kind of understanding when you have to use them, when it would be most appropriate, but that's kind of about it. Lastly, I have this classifying matter graphic organizer. So obviously at the top is all matter, and then between matter you have pure substances, of course, and mixtures. And as I said before, mixtures go into two subcategories, heterogeneous and homogeneous, and pure substances, which would be either elements or compounds. So between these two, it's just going to be physical changes, but between the elements and compounds, it's going to be chemical changes, right? So elements, anything on the periodic table is an element. Oxygen, gold, iron, lithium, carbon, anything, you name it. Not anything, anything on the periodic table. But compounds, salt, baking soda, sugar, water, carbon dioxide, those are compounds. So this is definitely a useful graphic organizer to kind of just keep that in your head in the very beginning of this introduction to chemistry. Kind of keep it in your head what things are. This is a very basic understanding. This is something that's just going to stay with you. You're not going to have to be like, oh, what's a pure substance? Is the mixture a pure substance? No, it's not. Like, this is something that once you get it, you're just going to have it in your head. It's just common sense. And I'm sure you know, if you do or if you don't, if you know a lot of this already, that makes sense. But that would be my first video for you guys. If you found this helpful, leave a like. If you're confused about anything, leave a comment. We'll definitely answer. And that is Introduction to Chemistry, beginning introduction, done. Thanks for watching this video and enjoy. Press the bell for other videos and helpful tutorials. Peace.